Willkommen, nein Sprache de Deutsch. So now I changed to English. Actually, you know, I've been in Munich all week, and I was in Berlin last Friday. I'm picking German words up at the rate of about 2 per day, so look out. Okay, so tonight we're going to talk about two things really. We're going to talk about the theory of caching. So this is some rules of thumb that should be quite useful for you to remember as you use caching systems. And then we'll actually go through JCache. Probably won't have time for a code demo, but I've got some code in the presentation. Just about me. So I wrote many years ago Ehcache, which is a caching framework you may have heard of. Then from about 2012 to 2014, I worked kind of part-time with Brian Oliver of Oracle from the Oracle Coherence team on JCache. We got that finished in mid-2014. And then also at the beginning of 2014, Ehcache was an open source caching project that I ran for about 7 years. And then I joined Terracotta. So Terracotta had got a distributed JVM technology. We kind of merged the two things together and created a distributed cache, which was quite technically successful. We actually pioneered a lot of technology there, including off-heap. If anybody's heard that term, off-heap, that actually came out of Terracotta. So we did some cool stuff. Another thing that we did that was quite cool was actually calculating the size of Java objects in memory correctly, taking into account all the different JVM settings and JVMs. So still hoping to kind of, that's actually all Apache 2 open source. So I'd like to move that into Hazelcast at some point. And 2 years ago, I joined Hazelcast as their CTO, and then unfortunately got promoted to CEO about 6 months later. So I've been doing less coding than I would like, but I still get to do a bit of this sort of thing. So caching is an interesting thing. Everybody knows about it, but I would say that I probably know a little more. I've done a lot of it over the years. It's got some interesting characteristics. Obviously, you do it for performance. The other thing that happens is when you shift load to a cache, it reduces load on the thing that the load was on before. So it tends to have the effect of actually lifting the scalability of the system. The other thing that happens is because you've reduced the load on the thing that you were using before, it actually also means that you don't have to make that thing as big. Now, you know, it means that you can run a smaller database. It's quite common to have up to a 90% reduction in database load if you do caching effectively, if what you're caching is the database. What's really popular, a really popular thing to do is actually put caching in front of a mainframe. Mainframes are really interesting because you can tune down the MIPS. So you can actually, even though you've got a piece of physical hardware, you put caching in front, and then at the next time you've got to update your MIPS, you can actually tune it back down. You can have a huge cost saving. So it's got that aspect. The other thing that caching does is it really uses the power of the machine. So you get amazing scale-up performance. And of course, with distributed caches, which is of course the kind that Hazelcast is and Coherence is, the two of us that wrote JCache, it's also about scale-out. So it's a technology that when implemented has all of these various effects. One other effect's worth pointing out, which is a buffer against load variability. So obviously, if you have a system with a fixed capacity and load reaches above the capacity, it'll cause degradation or an outage. Caches are more robust than most technologies at actually handling peak loads because it's very, very inexpensive to serve results out of memory. So there's a lot of stuff to do. The other thing is that caching, and it's even more the case since JCache, it's a technology that you can retrofit to an existing application. So it has all of these very interesting characteristics. Couple of things to keep in mind. You should only cache when you're going to use the data more than once. I mean, that goes without saying, but it's something worth remembering. The other thing is that if you've got something that's very inexpensive to create, don't cache it. Caching has got an almost zero cost, but not a zero cost. If something's cheaper, then don't do it. Some common problem areas, anything web scale. So I created Ehcache when I was at whatif.com. Whatif.com was like Kayak or Expedia or one of these companies. It had 85% Australian market share. We had 30 or 40,000 concurrent users. The company ended up IPOing and being worth a couple of $1 billion. At the time that I got involved with it as a consultant with ThoughtWorks, they were down 3 hours a day. They had an ASP web servers in front of the largest SQL server that they could run at the time, and they kept crashing the database. So we introduced caching. And if you look at any web scale architecture from all the big web scale companies, you'll see that they all have extensive caching architectures. The network's expensive, and the wide area network is even more expensive. So whenever you see a wide area network, great opportunity for caching. One example that I came across when I was at What If is we were talking, we had our data center in Sydney, and we were doing flight searches across to France. So we were talking to one of the GDS systems that was in France. It was about a 240 millisecond round trip. So by caching, we dropped the 240 milliseconds down to a couple of microseconds. And turns out that Brisbane, Sydney, Melbourne, in terms of having data that's used more than once, we're only caching for 5 minutes. So you might think to yourself, wow, there's so many flight routes in the world, there's no point doing that. It turns out Brisbane, Sydney, Brisbane, Melbourne, Melbourne, Sydney, Melbourne, Brisbane are 3 of the busiest flight routes in the world. So it was actually very, very valuable to do so. I don't know if number 2 is as important as it used to be. What I used to do in the past was use Hibernate, and there was Hibernate level caching, and then you would do a whole bunch of queries and you'd build up an object as what you actually wanted to do work on. I found that caching that was much more valuable than caching at the lower level. And then finally, anything touching a mainframe or a NoSQL. Let me clarify that. A database obviously has got scale limits. So one of the reasons that you cache is so that you don't have to change your architecture. Mainframe, there's an immediate cost saving, well, not immediate, but within a few months, like I said. NoSQL's a little different. NoSQL obviously has got no problem scaling. You would only cache there if you want performance. And actually, it's pretty common to actually combine with a Cassandra or Mongo, some cache. This is a pretty obvious diagram. The thing to note is that caches live in the middleware part in your Java app server, and they intercept the call that goes to the thing not being cached. In caching, the way it works is you can either write that code yourself, in which case what you do is you say, okay, I'm normally going to go here. Instead, I'll look aside and see if I've got the object already in cache. If I do, I'll short circuit that and come back. If I don't, I'll go out, I'll come back and I'll put it in. So that's called look aside or cache aside. That's one pattern. The other pattern is that you have the cache between you and the thing that you're caching. And then pretty much every Java caching framework that we're going to talk about tonight has actually got cache writers and cache loaders. Or the equivalent. So what you can do is you can go to the cache and say cache.get. If it's not there, you'll have a loader interface that you implement, which will actually go and load the data into the cache. And that's kind of a little cleaner in that you always read from and write to the cache. So that's called read through and write through. There's another cool thing that you can do for scaling write performance, which is that you can asynchronously write. So you can send a whole heap of changes to the cache. You can batch them up, and then you can periodically write them, but doing multiple writes within a single transaction. Databases tend to struggle with the number of transactions they can do, but they're actually pretty good in terms of actually writing to media. So so that's called write behind. So there's some terms for you. Now, surprise, surprise, we build caches out of RAM. If you're not building a cache out of RAM, it's not going to be very fast. The general building blocks is heap, obviously, but everybody knows the heap limitations. In fact, one of the primary reasons for running a really large heap is to actually cache. If you're not caching anything, then you can probably keep your heap pretty small. Then the next thing you can do is actually store data in the Java process hidden from the garbage collector. So I use the term opaque to the garbage collector. Now there's a number of techniques. We talked before about off-heap. So there's a couple of ways of doing off-heap. You can use direct byte buffers. So you implement your own memory manager on direct byte buffers. You can also use Sun Misc Unsafe. It's got some slightly different ergonomics. We at Hazelcast have even actually done opaque storage actually on the heap using an array of byte arrays. We call it on-heap slab allocator. We haven't put that in Hazelcast. We actually use Sun Misc Unsafe ourselves, but that's the series of techniques. From a performance point of view, the read and write from memory is exactly the same speed as reading to and from heap. What differs, of course, is that you've got to serialize and deserialize. That's the huge performance difference. And of course, obviously also, you really can't do anything with the object when it's serialized other than deserialize it. Everything below that actually you deal with in serialized form. So another thing, of course, you can do is you can have local storage. You can overflow to disk, rotational disk, which is very slow. You've got SSD. You've got in between RAM and SSD, you've got block addressable sort of persistent RAM. There's a whole bunch of different technologies. I've had a look at them so far. Like the one from Intel and the others, they all seem to be block addressable, so they're kind of in between. And then, of course, you've got the network. Now, across the network, if you want to make it fast, you actually just have this same hierarchy across the network. Just sort of some typical performance, just citing Hazelcast. So in process, so what we have is we have a grid, a memory data grid, which is across the network. If you've got to go across the network and come back for like cache.get, cache.put, it's about 140 microseconds. If you've got a 10 or 40 gig network using some fancy network cards, we use solar flares. You can get that down to 70 microseconds. Then we also have near cache, which is an eventually consistent copy of the data that's in process. And this is common in memory data grids to have this. And then the access time is less than 1 microsecond. In our own architecture, we have near cache on heap, and we have near cache opaque with high density, we call it. And then across the network, we have both of these as well. So in Hazelcast, you can create multi-terabyte caches. You can do that also with Terracotta. That's about the only two technologies that you can really reliably scale, in Java at least, to that scale limit. So there's an old saying that when all you have is a hammer, everything looks like a nail. Now, one of the things that you have to be careful of as programmers is that when it comes to optimization, you'll probably want to go and optimize your code. That may be a waste of time. Gene Amdahl, who died last year, he was a mainframe guy from the 70s. He created a computer company called Amdahl Computer. He created this law. There's the formula for it, but essentially what it means, and what I do whenever I'm doing performance work, if your response time is this, okay, what I do is okay, total response time is this, then I start measuring at boundaries to actually break that up into pieces. If you're going to optimize, try and actually optimize the biggest piece. And then the second biggest piece. You get the most bang for your buck. That's what this is telling you. So if you look at an entire sequence, that will help you to determine what you should cache. Now, caching is even though it's a relatively simple thing, it's subtle and it tends to be misused. I think there's a lot of people over the years, particularly with Hibernate, that turned on caching and thought they were done, and then they didn't really understand what was going on. Like I said at the beginning slide, don't cache something that you're not using more than once. Now, to really understand what a cache is doing for you, you have to look at the statistics. Now, statistics is actually standardized in the JCache spec. The key statistic is called cache efficiency. So that is for the total number of requests, how many cache hits you had, what the percentage is. So the higher it is, the more efficient your cache. If your cache efficiency is low, it could be that you want to make it higher, it could be that you want to, it could be low because you're only holding a very small percentage of the data set and you're holding the wrong part of the data set. These days, with memory being cheap and technologies like Hazelcast scaling, you can pretty much put as much data in the cache as you want. That wasn't the case before off-heap techniques and when memory, back in the 32-bit days particularly, but now you really can. The other thing, of course, is TTL, time to live. So if you've got a low time to live, the entries might expire out of the cache. There's a technique called refresh ahead, which refreshes entries in the cache before they expire. That's a technique that you can use for raising cache efficiency. One of the things that happens with caches, there's a couple of problems that you have to think about with caching. These are really the key problems that caching introduces. The first thing is that most people in their caching journey start out with no cache at all, and then they'll use an in-process cache. So Ehcache remains a popular choice. There's also Guava is another one. And you end up with an in-process cache. So, but of course in production, there's very few systems that actually just have a single app server. Anything non-trivial actually has an array of application servers behind a load balancer. So what actually happens is this thing called the n times problem. So each application server has to actually load its cache from the data source. You can generalize it to say that every time to live period, n requests will be made to the underlying system, where n is the number of application server nodes. So there's a nasty thing that happens. You build a system, it starts out small, you've got 2 servers, you put 2 in-process caches in, you've got 100 entries expiring, once an hour, and so you've got 200 requests, and let's say the data's getting used heavily, you've got 200 requests an hour. And then the system keeps growing, everything's great, database isn't hot, then the system keeps growing, and you get to 10 application servers, and then n times you get to 1,000 requests per hour. Now, in real life, if you actually have 50 or 100, maybe 20 or 50 caches, and you've got 5-minute TTLs and everything, you can have this linear growth to the back-end system. It comes as a huge surprise because people are like, hang on, I thought I had this problem solved. It's the n times problem. You'll know when you see it, you'll remember back to this talk and go, aha, I have a name for this. The other thing, of course, is that with caching, we're holding a copy of data. So we're holding a copy. Is that copy consistent with the ultimate source of truth, the system of record? So that's consistency with the system of record. That's a problem that has many solutions. The poor man's solution is time to live, which means the inconsistency window cannot be longer than the time to live. There's some hot cache techniques where you read off redo logs of databases and reflect those back into a cache. Perhaps the simplest technique is when you're doing caching to use the read-through, write-through pattern and just send everything through the cache, and then it will always be consistent. The next problem with a distributed cache is consistency with other cache nodes. So in JCache, we actually defined the simplest programming model, which is strong consistency. There's different cache technologies out there, and not all of them are always consistent with the other nodes. But for the JCache spec, we define it as strong consistency. You may want to relax that to eventual consistency. There might also be times where you just want weak consistency, just depending. But it is, as with all distributed systems, it's something we need to keep in mind. All right, so let's move on to JSR107. First of all, the obligatory joke about JSR107. So JSR107 took 12 years to complete. So it's the longest that any spec has ever taken, and it's been the butt of jokes. I only myself got involved about 6 years ago, and I did drive it to completion. They've actually since changed the rules. So the JCP 2.9 process will not let things live on this long, and in fact, there's a renewal ballot that now happens if you stop making progress. So we hold the record as the longest running ever spec. Proud of that. I mean, the idea is pretty simple. For a decade we've had different caching implementations. They've all got their own APIs. So wouldn't it be nice if we could agree on a common API? You could code to that. People building frameworks could code to that, just like we do in many other parts of Java. That is just a really simple idea. It felt like something that needed to be done. Recent history with a little bit of a Hazelcast slant. So we finished the spec in 2014. The spec doc's about 160 pages. I think it's a pretty good read. If you are using JCache, the Java doc's pretty good, but the spec is very, very clear and well written. It has many, many tables showing the correct behavior under various scenarios. Spring was very, very early to adopt JCache, which they did in September 2014. Spring continues to make improvements with its JCache implementation. At Hazelcast, that's the series of releases that we've done. The other thing that happened is between a few months after the spec coming out and for the next year, we saw pretty regular implementations from open source projects and commercial companies implementing the spec. So we're in pretty good shape there. Hazelcast itself, the main distributed data structure for holding data is actually IMAP. What we've been doing is we've been bringing more and more maturity to our JCache implementation from IMAP. So for example, just 3.6 release, we added split brain handler for what happens when you heal from a split brain. We also added quorums for preventing write operations if your number of members drops below a certain number to avoid problems. I need to find time to finish JCache 1.1. It's just an errata. It's actually a pretty good spec. There's very little wrong with it, but there's a few errata items, so we'll get that done. JCache is Java 6 and above, so it should work with anything you've got in production. Implementations. So the RI is actually not for production. It's really one of those RIs that's just for proving the correctness of the spec and used by the TCK. Ehcache, my old project, that's in good hands at Terracotta. They've got a very nice implementation. Obviously Hazelcast, where I am now. Oracle Coherence, who's arguably the market leader in in-memory data grid. They have a very good implementation. In fact, the Oracle Coherence team implemented the spec in the last 6 months when we were finishing it off. So we actually had the benefit of having a very sophisticated in-memory data grid implement the spec and find problems with it, and that led to a much better outcome. Infinispan JBoss data grid. The other one is the Russian guys from GridGain, who've also just open sourced GridGain as Apache Ignite. They've got both actually. They've got GridGain as their commercial version with some enterprise features plus Apache Ignite. They implemented the spec very early. These guys, there's a .NET in-memory data grid the company's called Ehcache. They have created a brand new pure Java in-memory data grid, which they announced at Java 1. It's called TaseGrid. That also implements the spec. So, you can see what's going on, right? I mean, this thing's ubiquitous. This is what we want. We actually want all of these choices. So, I'm really pleased. Ben Maines. So, Ben Maines is a very bright guy that works at Google. He caused me a huge headache when I was implementing Ehcache 1.6. He had this, what was it called? Linked concurrent hash map. And it was designed as a caching primitive. Anyway, it wasn't thread safe. I was on a cruise and I tested. I used to have my tests fail occasionally. I'm like, there's something not right. And so I set up run after run after run. Eventually, I was able to get his thing to fail in about 2 minutes. So I proved that his code was not thread safe. So with Ehcache 1.6, I then went back and did my own. I got about a 50 times speed up in Ehcache back in the day. But anyway, he's kept going. He's been working on Guava while at Google, and he's created a new in-process cache called Caffeine. So it's not distributed, it's in process. Unlike Guava, which does not implement JCache, Caffeine actually implements JCache, and it's quite a bit faster than Guava. And actually, at the moment, it claims to be the fastest in-process cache. So it's actually worth a look. It's a brand new one, and we'll keep looking at these as they come along. So that's the good news. I have one company to complain about. Gemfire, Pivotal Gemfire. These guys, they really, as commercial and memory data grid, they've really been in the number 2 position. They have not implemented, and they don't want to implement. They're integrated into Spring, and obviously Spring's very important. And they're part of the same company as Spring, so they have no plan to implement. I do have on Twitter, Pivotal JCache hashtag campaign to give them some feedback. So if you feel like we should have 100% implementing the spec, this is the last holdout. So put some pressure on. Now, let's just talk about NoSQL for a minute. Some people use NoSQL for caching, and there's Java drivers for NoSQL. So what's going to happen there? Well, you really can't implement the JCache spec in NoSQL. The guys that have come the closest are Couchbase. They've got their developer preview 2 out. I talked to them at JFocus last week. They think they'll finish, but they're not going to be able to pass the TCK. But you'll still be able to use the basic API, which should mean that Couchbase, given that Spring and so on really just uses the basic API, you probably will be able to use Couchbase behind a JCache interface. I haven't heard anything from the other NoSQL players. As I was saying before, even though NoSQL scales out, it's relatively slow compared to caches, something that's designed to be a cache. So one just like with the database, a great way to actually use NoSQL is to actually use read-through and write-through. JCache has actually got a cache loader interface and a cache writer interface with single methods and also batch methods. So you actually just implement your driver to that. I think one of our solution architects actually did that for Mongo, for example. It's up on Maven. Now, we're just going to go through the essential core concepts of JCache now. So the first thing is to anchor, is to think about map and to think about JCache and what the differences are to map. So they're both key value based. JCache has optional support for an implementation to enforce types. So if you configure that, which you're allowed to do on the spec, you can then throw an exception if you put the wrong types in. So it means that you can have schema enforcement. Java util concurrent map methods. We actually, they don't have the same names, but they do have the same. We've got equivalents of each one of the atomic operations, and the compare and swap is it's another alternative consistency model to strong consistency that's supported in the spec. A map is designed to be in process. Actually, where's Jan Genser? Is he in the audience? There he is, back there. So he's been looking at Java Util Stream, and we're actually building a distributed version of Java Util Stream at the moment. And he was saying that that nothing in Java Util Stream is serializable, right, Jan? So it's written as an in-process API. The same is true of map. Now in JCache, in JCache, everything's got to be serializable. The other thing is that in map, obviously, nothing goes away unless you remove it. Caches are different. TTL, a time to live, is an essential concept of a cache. As I said, it's a poor man's way of eventually becoming consistent with the thing that you're caching. So entries do expire. We have various expiration policies, including eternal, but eternal's the exception. They do expire. Now in map, entries are on heap. Obviously that goes without saying, like most things in Java. In JCache, we allow things to be stored anywhere. So when I showed that pyramid before, we support all these different topologies. So the main way we support that is by not assuming that the entries are on heap. With that in mind, when you put something in a collection in Java, if you actually hold a reference to the thing you just put in the collection, and then you mutate the object, it actually also mutates it in the collection. This kind of screws with people's heads. Now in Ehcache, we always allowed that, and most in-process caches do, and it's a misuse of the idiom to put something in a cache and then hold a reference to the object you just put in and mutate it in the cache. But it's fast to do that. What we do in JCache is that the default is not, even when you're using just on heap, is not store by reference, it's store by value. What we mean by store by value is not store by reference. So we mean any technique which means that if you keep hold of a reference after you just put it in the cache and you change something, it does not change it in the cache. Implementer is free to use any technique that achieves that contract. So this avoids that confusing side effect. However, for performance, store by reference is obviously the fastest thing to do. So we allow a cache to be configured store by reference. We explicitly support integration with cache loaders and cache writers. And we also support observation. So we have cache entry listeners, and we listen for a multitude of different events. Add, update, remove, and then a special one, remove all. So you can also clear a cache, which doesn't trigger an observer, but we have a special remove all event, which is efficient to implement, that actually will tell anybody that needs to know, any listeners, that we've actually just zapped the cache, and then you can take action. And we support statistics, standardized statistics. Put your hand up if you've heard of an entry processor. Yeah, not many people. Oh, Paul Salazar, our sales guy. Paul, please explain an entry processor to the audience. Nine Dunker. So, working with Brian Oliver for a couple of years, I came to realize that that in in-memory data grids, the workhorse, the thing that's used the most, is entry processors. It really is a very magical thing. The way it works, imagine you've got an in-memory data grid with all these nodes, and then you've got your app server over here. The way that caching works is that you go get, you do something, and you go put. If you, let's say you want to lock that entry, because it's like in a database select for update. Let's say you want to do something like that. So in Terracotta, we had, cache.lock key, cache.get, do something, cache.put, cache.unlock. So 4 operations, all of which have got to go across the network and get written to backups. Now with an entry processor, what you do is the code that you're going to execute in your app server, you install that code, your code, over in the in-memory data grid in the nodes, and then what you do is you say cache.invoke, and you pass in a key, you pass in the entry processor that you want to execute, and then you pass in some arguments. So it's a command pattern, and in an in-memory data grid, there's consistent hashing, so it knows which node it is. So it goes across the network with this tiny little 40, 50 bytes of what you want to do, and then over in the node, in Hazelcast we have a partition thread. The partition thread will lock it. It'll lock it. It'll do whatever you want to do. Entry processor's got like read and set. And then when it's finished, it intrinsically unlocks it. So all this can happen in a node in a matter of a couple of microseconds. So you eliminate you replace 4 network hops with 1 network hop. So this is mind-blowingly faster than doing traditional caching. So really fantastic idea from in-memory data grid. So I did not want to pass up the opportunity to add this to the spec. So it's in the spec. Let me just see what else we have here. Obviously, it goes without saying, full generics. And because we have entry processors, we did not see the need to actually add a lock API, which is very nice. So there's no locks defined. Topology agnostic. Being topology agnostic actually has some interesting consequences. One of the things that you would expect that we would define in a cache API, given that a cache always has this concept of a capacity, and when you get over capacity, so you'd set a size, and when you get above that size, then you would evict. The thing is, in an simple in-process cache, that's a pretty simple concept. In the more sophisticated in-memory data grids, it's a little bit elusive because you have multiple stores. So over in Terracotta, we had near cache on heap, near cache off heap. Then on the server, we had on heap, we had off heap, and we had SSD. So we've actually got 5 different stores that can hold data, and each one of those needs to have a capacity configured for it. So it's not really possible in a spec to actually configure storage limits unless you also actually define the different resource types. So we chose not to do that. Let's have a look at the key classes and interfaces. So we have a class called caching, and this is your bootstrap class. We use the service loader concepts. So you add a implementation to your class path, and you do caching loader dot get caching provider, and then it loads and tracks a caching provider which implements the SPI, and then with a caching provider is the Hazelcast JSR107 or the Ehcache or the coherence, and then you can then create cache managers. Now, to use a database metaphor, a cache manager is like a database, and then a cache is like a table. So, and this is like kind of an installation of Oracle. So you can create multiples of these, and you can create multiples of these. Now, caches actually have entries, and there's a sub-interface of entry called mutable entry that we use in entry processes in cache. A couple of things to point out. We support having multiple caching providers in the class path and actually being able to select between them. That's quite useful. What else? There's all sorts of convenience methods. So you can just do, if you can do caching.getCache, and it will actually use the default. It'll actually, this works when there's one caching provider on the class path. It'll just do under the covers. It does caching provider.getCache manager, the default.getCache. What else about Cache Manager? One interesting thing with so in an in-process cache like Ehcache, when you create a cache manager, it will actually create all of the caching infrastructure that's used in process. When you are using a distributed cache, like Hazelcast or Coherence, the cache manager and its caches actually live independently of the scope of your application server. So when you go create or get cache manager, it actually essentially just connects you to the caching infrastructure. So there'll be so we don't define any configuration in JCache. The configuration is left to the implementation. So the configuration will be consulted, and you will connect to the caching infrastructure. It's like having a once again, the Oracle metaphor. It's like having a database client and connecting to a database. And then also, once you shut down a cache manager in a distributed context, you're not shutting down the cache infrastructure, you're actually just disconnecting from it. All right, so we've talked a lot to get to a simple example. Here it is. This is pretty much the sort of code that you'll see. So cache manager is caching.get cache manager. This is very similar to Ehcache, surprise, surprise. I quite liked it. We have a cache, key of integer, value of string. And then we get the cache, and then we pass a hint to the implementation that we want type enforcement. Then it's just a put and get. There's many other methods, but they're very much like the map methods, and that's pretty much the guts of it. Entry processors. So this is an example of an entry processor, cache.invoke, and we create an increment processor, and we pass in the value 42. So if that's in a distributed cache, what will actually happen is that you create one of those over in your app server, and then what actually happens across on the node is it actually uses one over there. So it's actually not using that instance. That doesn't get passed over the wire. Well, we only define, this is only defined in Java 6, so we haven't specified that one way or the other. The other thing that's worth pointing out, in terms of code that you want to execute related to a cache, you've got cache loaders, cache writers, you've got listeners, you've got expiry policies, and so on. When you're using the cache API, you always pass in a factory. The reason you always pass in a factory is because in most distributed implementations, it's more efficient for that code to be actually executed in the cluster. It's not going to be executed in your app server, so everything's defined as a factory. And the thing will be, it's up to the implementation where that thing, the instance of the thing you define, gets created. In the case of a cache loader, you might actually have one instance actually per node. So it's very much left to the implementation. And we do things like in the spec, we say, in the case of a listener, we say that an event will be observed once across the cluster. We don't define where that is observed. It's left once again to the implementation. So there's kind of, to accommodate the huge variety of implementations from simple in-process to the most complex distributed ones, we sort of do things like that. That's what an entry processor looks like. So this is the increment processor example that I gave before. So there's just the interface to implement as process. It takes in a mutable entry, which is a sub-interface of entry, which has got mutative methods on cache entry. And this this illustrates the examples of entry processes. I think I mentioned this. It just eliminates the round trips. And that's what entry processor replaces in terms of the four methods. Going back to Ehcache days, there was a guy called Eric Dahlquist that added Spring annotations for Ehcache. We went back and defined those in JSR107. We worked with Eric and a bunch of other people. We came up with some new annotations. So they're the annotations that we have. What's happened is that Spring has its own annotations, and when it added support for JSR107, it added our annotations as well, and you can mix and match the annotations. So it's nice. Over to Spring. Who uses Spring Boot? You people, yeah. So if you've played around with caching in Spring Boot, you know that all you got to do is drop a JCache implementation, a provider into the class path, and it auto configures it. We also, which is nice, actually for Hazelcast, it's also explicitly looks after Hazelcast as well. But Spring's continued to do a great job of embracing JCache, and therefore I think there's probably a lot of developers, using JCache and using the JCache annotations as a result. EE situation is not quite as healthy. 107, we missed the deadline for EE7. Now EE8 is still going. I'm trying to get this kick-started at the moment. There's a guy called Adam Bean. Has anybody heard of him? Yeah. So Adam is volunteering to lead the effort to add JCache to Java EE8. I talked to him last week at JFocus, and he's got a group of about 4 people that are helping. They've got a prototype done. They've got a Slack channel. So I've commenced the extremely painful process of talking to Bill Shannon, who's a Java EE architect, and trying to kind of get him moving on this. So, hopefully, I didn't have I would love to see it happen. It is quite painful doing a JSR. Doing a JSR involving the EE group is kind of quite painful, and I think really it's probably quite hard to do it unless you work at Oracle and have these contacts with them. So anyway, I've kicked it off, and I've had about 10 emails back and forth to Bill, trying to kind of get him revved up to the idea of looking at the spec and telling me if there's anything that he needs changed to actually put it in. So there's just a huge difference between the Spring community and the EE community. But there are still people that use EE, and if once again, like Pivotal Gemfire, if we could get it into EE, we'd actually have a clean sweep. So I'm very keen on doing that. JCache 1.1, as I said, I should get that out. EE, hoping for. In terms of what we could do with the spec later, pretty much every in-memory data grid uses transactions. They're not used a lot because they're slow, but there is a time and a place for local transactions and XA transactions. I did define, we did write a chapter on this, and we added, it was a pretty minimal API change to actually support transactions. I actually did this with Ludovic Orban, who's the maintainer of the Bitronics transaction manager. So this guy knows a thing or two about transactions. So I think we did a pretty good job. The issue was, and we added it to the spec, and actually pretty much most of the real-world implementations could have easily implemented it. The issue was that the reference implementation didn't have it. It's not, as I said, it's not really a full implementation, and the rules are that you really need to add that to the RI. We just didn't have the time to do it, so we left that out, unfortunately. Another thing, last year with Peter Laurie, I designed an async API for JCache, which is nice. Like in Hazelcast, we actually have on our iCache, which extends JCache, we actually have an async API, that's too much to add into 1.1, so it's got to wait for 2. And then I guess another idea with servlet was Servlet 4.0. You know, I've probably got the energy to do 1.1. I'm about 70% done actually, and then there's a pretty active community around JCache. So I do think that JCache 2 will get picked up and delivered a few years from now. So a couple of slides just on Hazelcast, JCache. Couple of things that we have. So Hazelcast, like most in-memory data grids, supports an embedded mode, which is very easy to use, where each member lives inside your app server. It also supports client-server mode, where you've got a separate cache infrastructure. JCache is implemented in both modes. So we have JCache in our Java client. We also have JCache in our member. We have a high density, we call it high density memory store. It's an off-heap technique for putting large amounts of data in. So we support that for JCache in the members, and also in Nearcache we also support HD. So it's possible to have 10 or 20 gigabytes of Nearcache data in Hazelcast for like pretty crazy performance. The other thing that we did to support really large caches is we created this hot restart store. That just came out in 3.6. So on SSD we support 300,000 writes per second per node, and then restart time we load up at 1.3 gigabytes per second per node. So it's very quick, and the combination of all those things will let you create giant caches should you wish to do so. We believe that we are the fastest JCache implementation. If you go to our website, we actually have benchmarks, and we've used Ignite's yardstick benchmarks. We're faster than them. We've used Radar Gun from Infinispan. We're faster than them. For Oracle coherence, we don't publish a benchmark because it's a breach of the Oracle Technology Network license. Instead, what we do is we let you download a benchmark and run it, and you can guess what the result is. What else? We've done a benchmark against Gemfire, and we're faster than them. And so the guys from GridGain, what they did when GridGain Ignite, so we were slower than them, a lot slower than them a year and a half ago. So we put about a year's worth of work into a lot of hard work to make ourselves fast. And we were using our competitor benchmarks as well as our internal benchmarks to kind of see how we were doing. And then, eventually we got faster. Now, when we released our benchmark against the GridGain Ignite guys, did they go and actually make their implementation faster? No. What they did is they changed their benchmark. So all sorts of esoteric and weird stuff. And the thing, of course, we care about is the central API of put-get. So we just recently, the last couple of days, actually had a look, and what we've discovered is that they're claiming that they're faster again. What they did is they were using so in the JCache spec, what we do is we're mindful of performance at all times. So in map you've got map put, and it actually returns the old value. So in JCache we have cache.put does not return the old value. We have got cache.getInput, which actually returns the old value. So you incur the cost should you wish to. So what they did is they were comparing our map.put, which returns the old value, with cache.put that doesn't return the value. So we changed ours to map.set to make it apples to apples. The other thing they did is in-memory data grids, you store multiple copies of the data. So we had, so they're called replicas. Now you can either synchronously write the replica or asynchronously write the replica. So obviously it's faster to asynchronously write to the replica. So they were using asynchronous replicas, and they had us configured as synchronous replicas. So it's just a ridiculous fake benchmark. So I've actually done a blog tonight. This may become controversial. I'm actually sending it to InfoQ, and I'm accusing them of creating a fake benchmark. When we corrected those two errors, we were once again way faster than them. So, it's I don't mind fair competition, And you know, one of the things that's interesting, once you have a standard spec, it basically invites people to compete in other ways, like in performance. I think it's good. It's good for you guys. It's good for you guys. So we have a question.
Yeah, are the tests on a single machine or is it a distributed test? Like, how do you test that?
All of the radar gun and yardstick tests are all tests on clusters. And if you go to our website and even my blog, like Danny, our test guy, always puts down his test configuration and the source code so you can rerun it. Doing a single node test is a bit pointless. There's something interesting about single node. Hazelcast is not an in-process cache. You can create with JCache or without. You can create a Hazelcast cluster of one node embedded. You might say to yourself, "Ooh, that's an in-process cache." You will be absolutely devastated by the performance because it's really bad. We do not even attempt to do any local in-process optimizations. We kind of thought about it, but then you've got projects like Caffeine from Ben Maines that's really pushing the envelope of what you can do in process. I think it's a different problem. I'm Greg R. Luck on Twitter, and I'm Greg at hazelcast.com. Can I just get my colleagues to stand up? We've got a few people in town working on a research project this week. Just make some introductions. Gentleman on the left, that's Ehcache. He's our Director of Engineering. He knows a hell of a lot about this, probably more than I do. Guy next to him, Jan Jensa, and Alexander Toktarov. So my colleagues, and also up the back, Paul Salazar. All right, well, thanks, guys. That's it. Oh, yes. I have 5 T-shirts for 5 questions. If I don't get any questions, I'm giving these to my colleagues. They don't need any more.
So there are different caching strategies, like first in, first out, least recently used, not least used. Is this configurable?
These are eviction algorithms that are configurable in JCache.
So is this programmatically configuration? Is it being configured via programmatically, like how
you can define the in JCache you define it in the configuration. We have about 5 strategies that we allow.
JCache or Hazelcast?
JCache.
But you said the configuration is but provided.
There's no.
Isn't there?
There's no
check
for eviction.
I get confused, between Ehcache and Hazelcast and Terracotta.
No, in JCache, actually the detailed configuration isn't part of the spec.
No, it's everything's the there is a configuration which is programmatic only.
Yes, but
so we have a class called mutable configuration. It's been 2 years, guys. You've got to give me a break on this. Right. We only in Hazelcast. In Hazelcast we don't actually have. We have a couple of configuration policies. In Ehcache we have LRU and LFU, and we have custom eviction policies. It's a feature that we're adding into Hazelcast this time. In the spec itself, we only define expiry policies, not eviction policies. Okay. So I'll give a T-shirt to you. And a T-shirt to you for correcting me. Sounds like you've been... I'm going to check my code or the spec first before I answer this time. Okay. All right, the gentleman up there.
So you've got like markers for different regions, like what regions and what data center data lies. But can you specify like... this data is very important to get fast, and this data is not
Well,
that important, so it can have some delays.
Sorry, just run that past me again.
So like, you've got different types of objects. Some options are more important than other objects. So in your slides you said you don't have an annotation for slow stuff like hard drives or fast things like your.
Right. So the way, we don't define storage tiers in JCache. We also don't define eviction policies, but in most real-world implementations, the most commonly used one is LRU, least recently used. Then that's followed by, sorry?
But you have got an annotation for data centers, like something like that. There was something on the slide where you can mark certain. What? I'm not sure.
I'm not trusting myself now. Let's go back and have a look. The annotations that we have.
Something for data center, or I think it was.
That's the annotation one.
No, not Java annotations, but what was in the text. So, back. Yes, scoping. Provides case scoping, say in a cluster.
That's the cache scoping. What do we mean by cache scoping?
I think what I've understood is that you can mark certain nodes as, don't know, region A, region B or something.
No, you can't do that in the spec. I can't remember what we had in mind when we put that in 2 years ago. In terms of any implementation that you're likely to come across, what you're most likely to find are built-in expiry policies, being LRU and LFU. You can also have eviction policies. You can also have custom eviction policies, where if you know more than we do about what should be kept in the cache and what should be thrown out, you can implement that. An innovation that I did in Ehcache that we've actually implemented in Hazelcast JCache, and we're actually adding to map this release, is a probabilistic approach, which is much higher performance. So if you relax the contract if you think about LRU, to actually really know the least recently used, every time there's a read or a write, you've got to rearrange a tree. That's expensive. The approach that I took in Ehcache, which we used at Terracotta and we're also using at Hazelcast, is statistical sampling. So what we do, we relax the contract. It's no longer least recently used. It's less recently used. It's no longer least frequently used. It's less frequently used. And what I did in Ehcache is when you get full and you want to evict, you randomly select 15 items, come back to 15 in a minute, and you then apply your policy to those 15 entries. And then you evict the best one. There's some corner cases, you don't evict the thing that you just put in, some stuff like that. That is a constant time evictor, and it's also very good because you really just, all you have to do is compare entries. And so all a policy is comparing entries. So in most implementations, metadata is stored along with the entry, so the access counts and so on. So if you random select 15 and you wanted to use an LRU, you just go through the last access time or the write time to find out which is the oldest entry and evict it. It's very simple and it's constant time. So we've used that. We use that at Hazelcast as well, and then we'll be adding it to map. The 15 gives you a 95% probability that you'll evict something from the best quartile, which turns out is good enough. I made this change in Ehcache about 7 years ago, and so far no one has actually noticed or complained that we're no longer deterministic. It's a beautiful performance optimization. Yeah. All right, so let's get another question. By the way, if the shirts are the wrong size, just swap with somebody else. It's an optimization I'm not looking after.
Okay, I have a question. Why need a need for entry process? Means all of the machines which are participating in a cluster, they can expose a part of their memory, and then every other machine can directly access that part of the exposed memory and can read and write from that memory card. So why there is a need for entry process?
I think I know what you mean. So what you're saying is if you have a grid and the memory is accessible across the network and you can simply get and put things into the memory.
We have a grid of 30 machines, and every machine exposes, or you can say 2 MB of memory for every other machine.
How are you doing that? What framework are you using for that?
When you are creating the cluster, then at the cluster creation time, they can expose some part of their memory to the other.
Sorry, which framework, which software are you using for that?
No, I'm talking about the Hazelcast perspective. Means you talk about the entry process in the Hazelcast perspective. So I'm talking about from the Hazelcast perspective.
Okay, so from a Hazelcast point of view, and what we do at Hazelcast is really no different to any of the other in-memory data grids. This is pretty standardized. So you have a cluster of machines. You've got memory essentially across the network that's available to you. So you can, Hazelcast, there's a lot more to the APIs than just caching, of course, but in caching it's basically a get put API. So you can do a get and it'll go across the network to that memory and bring it back. So the question is why isn't that great? Why therefore do you want to use an entry processor? Okay. So let's take a trivial example of I don't know, incrementing or decrementing inventory. Okay, so let's say you've got toy 26. Okay, so you go cache.get toy 26. It'll actually find which node it's on, does a single call across the network, brings the data back. The data is already stored in binary form in Hazelcast, so it's binary, goes across the network in binary, and then we just deserialize it once. That's quite efficient. Then we decrement it, and then we put it back. In that case, because you're performing, because you're actually mutating it, what do you want to do? What do you want to do with other threads? While you're actually making this change, what if you've got multiple threads that are actually all trying to decrement inventory? If you just decrement and put it back, you'll have races and you could actually lose decrements. One solution to that is to use the compare and swap API. So if inventory is at 26 and you come back and you want to decrement it to 25, you do cache.replace and you do the key, and then you do old value 26 and you do new value 25. If in the meantime somebody else has decremented, then that will fail and it won't be applied. So that solves that problem. But what if it's more complicated and you want to lock it? So you don't want anybody accessing that at all. You want exclusive access. Then in Terracotta, or actually even in Hazelcast, in Hazelcast in map we have lock. So you would call map.lock, which you'll have to go run across the network to the and then it'll return, and then you do get, and then you make your change, you put that back in, and then you unlock. So it's four separate processes. If you use an entry processor, you can achieve all of those 4 steps in one, and you haven't had to bring the key and value across the network. All you've sent across the network is cache.invoke, key, decrement processor, and 1. So that's all you've had to send across the network, so it's much more efficient. Okay, I've given you your shirt. Okay.
So, follow-up question. So the entry processors are executed in order, one after the other. Otherwise, you would have the same problem, right? So if two actions will try to decrement, and both send invoke decrement value, they get executed one after the other.
If the way you would write an entry processor for this is you do mutable entry.get value, and you'd read the value, and then you'd decrement it, and then you do set value. That's all happening atomically. So the entry processes, even if they're racing on the same key, they get serialized and they get executed one at a time. It's a really cool idea. The Oracle Coherence team invented this, and it's become universal. So that's why we standardized it. All right.
Yeah, in your code sample of an entry processor, you showed that it can be used for an explicit or for a specific entry within the cache. Is it also possible to use it for bulk operations?
Use it for what?
Bulk, as in for modifying?
Yeah, we do use it for bulk. However, there's no... we can use it for bulk, which can be more efficient than just iterating through a loop and calling entry processor, calling invoke. So there is a batch method. The programming contract is that the entries are only locked one at a time as they're executed. Also, if you use a batch method, there's no auto guarantee, because in most implementations you'll have the keys will be distributed across the cluster. So if you actually do cache.invoke with a batch, then a lot of them will actually be executing concurrently. So there's no auto guarantee. But yes, there is a batch method. There's batch methods generally in most of the APIs in JCache.
Sorry, one last question. In the roadmap, you mentioned that 1.1 release is just a maintenance release, and in the planned JCache 2 version, I didn't see anything about streams or MapReduce or anything along those sort of lines. Will there be any support for this, or is it planned?
What do you mean by stream? Do you mean Java util stream, or do you mean something like that's more of a hot source? Do you mean Java util stream?
Exactly, yeah.
Okay. Unfortunately, I mean, Java 8 was around when we were doing this. Unfortunately, I mean, it was a design choice. We did want to support Java 6 because we knew that the spec would be, immediately implemented and usable, and we want it to be used in real systems. Probably JCache 2 would actually up the version to Java 8. Not sure where that would lead. I mean, one thing that we did with listeners, we have functional interfaces, so we broke there's observing a put, there's just basically one method per interface for lambdas. So we sort of took care of things like that, but we haven't. Yeah, we would. I mean, the other thing we did, although I didn't mention it, is that cache itself is iterable, and so we've all of the concepts up to all the sensible concepts up to Java 6 we've included. But yes, JCache 2 would likely, when it gets done, given that 9 will probably be here and 8 will be widely in production, we'll actually up the minimum version to Java 8 and look at integrating stream. Yeah, I think that's probably pretty likely. You haven't asked a question, but you're dying to. All right, I got one more T-shirt, one last one. Ennis, what would you like to know about JCache? You. Okay, here we go. Whoa.
You mentioned at the beginning the end problem. Maybe I was somewhere in the process. How is that handled usually? So you have end nodes there, and they just go across the network, or?
So you want me to re-explain the end times problem?
No, so end times problem is that you have end clients that are using cache and are querying something. But how is that, how solution is used distributed cache? The line.
Yeah, the solution's a distributed cache. So it's all right, you get the T-shirt. I actually think you made a point. I don't think I actually mentioned the solution. I mentioned the problem, but not the solution. So the solution is a distributed cache, yeah. what was nice for me, so Ehcache, which is an in-process cache, the Terracotta guys came along and we turned it into a distributed cache. That was nice because I didn't have to do that. Ehcache still actually has replicated. It has a weekly consistent replicated mode, which is quite okay for non-changing data. And then, of course, Hazelcast, what was nice about Hazelcast was that was already a beautiful distributed cache, and then we just added JCache to it. So yes, I'm all about distributed caches these days, not in-process caches. In fact, as I said, we are a terrible in-process cache. And we don't really have any plans to fix it because we're not in that business. Yeah. All right, well, I'm done with T-shirts, and my voice is just about given out. And I've humiliated myself once, getting something wrong, so I might leave it there. Thank you.